Hi, so welcome. Today we're going to talk about 5.3, integration by substitution, also called use substitution. So let's start by remembering a recap about fundamental theorem of calculus, which we talked about last time. So remember, we were interested in finding the integral of a function between a and b. Just remember what that looks like. Here's my function, here's a point a, here's a point b. I'm looking for the area under the curve between a and b. So something like that. In the past, we only knew how to do this with a Riemann sum, and that was like this. We break it up into rectangles and we kind of approximate it and imagine taking a limit. The great thing about fundamental theorem of calculus is that we don't have to do any of that process. We just have to look at our function f, find an antiderivative for f, and plug that in. Plug in your b and plug in your a, and subtract. And it turns out that's enough to get the area. So like, for example, I might know that x squared, its derivative is 2x, right? So if I'm trying to integrate like 2x from, say, 1 to 4, then I can do that because with x squared being my original function f, I can, sorry, if my original function f is 2x, I can find the antiderivative, x squared, a function whose derivative is 2x. And I can plug my numbers into the big F instead as a way to evaluate this. So as long as I can identify the right big F, the antiderivative of my inside function, then I just plug in my 4 and I plug in my 1 and I get something. Here, since our original function was 2x, we can identify the antiderivative as x squared. It's something whose derivative is 2x. So big F of 4 here is 4 squared. So I'm plugging the 4 in for the x, and then 1 squared. So we get something. We get some number, and that's the area under the curve. So this is awesome, right? We can do integrals by doing antiderivatives. The hard part is actually coming up with this step, with the antiderivative, right? In my example here, we started with x squared because we already know its derivative. But if I just hand you like a random function, x times sine of x or something, maybe that's my function, I want to integrate it. How do I come up with an antiderivative for this? Right? That's the hard part. So a lot of the rest of the class is going to be how to find an antiderivative given your function. The most important and basic technique that we're going to talk about today is use substitution. After today's lecture, you should always be trying use substitution first. It's like the most common and most important thing. If you know any integration method, it should be use substitution. It should be the first thing you think of to try. A lot of times, it ends up being a little harder and use substitution doesn't work. And in that case, there's these other techniques we can try. But number one on your plate should always be use substitution, and you should feel really good about how it works. Okay, so let's talk about it. So it turns out use substitution is to do with the chain rule. So let's kind of remember how the chain rule works from regular calculus. So the chain rule is this thing where I want to take a derivative of not just sort of a function by itself, but something that looks like a nested function, like a function inside another function. So for example, if we look at this function, it's the square root of x squared plus x plus 1. So, right, I can think of that as like, okay, I have square root of something. Square root is like a function. And then I have this x squared plus x plus 1. That's sort of this inside function. I could imagine, if I'm going to plug a number into this formula, one way to think about it would be, okay, I'm going to start with my number x, and then I'm going to square the number, add the number, and add 1. And that's like applying the inside function. So for example, if we started with like 2, we would go to 4 plus 2 plus 1, and we get some number. In this case, we get 7. And then after that, I like apply square root to what I got. Right? So it's useful to think of this as a two-step process. I first apply, like the x squared plus x plus 1 function, and then I'm going to apply like the square root function. Now I'm going to write square root of x here, which is a little bit confusing because there's a lot of x's going on. But remember that x always stands for like the input. So if I label this arrow square root of x, it's saying take the square root of whatever the input to the arrow was. So if here my input is x squared plus x plus 1, then I apply the function square root of x to that. That means plug the input anywhere where the x is. So the input happens to be x squared plus x plus 1, and so my output is square root of x squared plus x plus 1, that input. It's confusing because I'm using the same letters, and I'm doing that because it's common, and so you kind of have to get used to it. But it would make just as much sense if I said, like, okay, I'm gonna start with something called y, say, first apply the function x squared plus x plus 1. That would mean take my input y and plug it wherever the x is. So I'd get y squared plus x plus 1, or plus y, sorry, y squared plus y plus 1. Meaning, because I just put y wherever the x was. Then I could apply the function square root of x, which means take the input, put it wherever the x is. So I get square root of x, square root of my input, so I get square root of y squared plus y plus 1. So you can imagine writing it that way too. The point is, if I call this square x squared plus x plus 1 function g of x, just to have a name for it, it's some function of x. I call this function f of x, just to have some name for it. The of x notation is just talking about input and output. Like, it doesn't have to literally be the letter x. So f here, it takes some input, and the output is square root of whatever the input was. And since this x represents whatever the input is, the x that's here is also just means whatever the input is. Right? If we continued our example with just the number here, 2 goes to 7, and then I'm applying so I applied the x squared plus x plus 1 function. Whoa, sorry. And then I'm applying the square root of x function after that. So I take my 7, and I do square root of 7. So hopefully you can kind of see the structure here. It's a two-step process, and that's what I mean by like a function inside another function. I'll just mention right away that it's not always like there's multiple ways to think of a sort of total combined function as being broken up into two steps like this. For example, we could take the same final formula and imagine like the first step being like apply like the x squared plus x function. So we get x squared plus x, and then I could have the second step be, well, what would I have to put here? Right? I want the final result to be square root of x squared plus x plus 1. I need to build that algebra result out of starting with this as an input and then doing something to it. So the answer is I'd have to do x plus 1 inside the square root. Right? This means this function is take the square root of my input plus 1. X is just my input. Again, these could be y's here, right? Or 2's. So if my input is x squared plus x, I'm kind of calling that x for the second. That input goes here, replaces that x, and then it's plus 1, and I do the square root, and I get this as the final result. So there's multiple ways to break up my like nested function as the exact like way that you've nested it. Usually for these problems, it's kind of written to be sort of like obvious. Like here, when I see this, I'm like, okay, that's the inside. That's like the inside function. That's like the first step. But it's possible to do other steps. Okay, so right, I use this f and g right here. So notice that we did this two-step process to go from my original input. Let's actually maybe go up here. Call this one g of x. Sorry, it's okay. G of x, and I call this one f of x. So we did this two-step process. Like we did g and then we did f. So the original function is kind of jumping all the way to the end, right? It's combining the two steps into one step to go just straight from x to the function, to the output square root of x squared plus square root of x plus x plus 1. So the way this people usually write this, you can write a single function name for this whole step, and it's like I took x, and then I did g to that x, but then what I did f to the result, right? Oh, I'm sorry, I probably should have labeled. G is here. Sorry, that's confusing. F is here. So I started with x, I applied g to get to the middle step, but then I applied f to whatever I got out of applying g. So it's f applied to the output of g. So the chain rule is how to take the derivative when you have a situation like this. When I have like a multi-step process, f of g of x, how do I take the derivative of that? And the formula that you may have learned from Calc 1, so I'm going to take the derivative of this, looks like f prime of g of x times g prime of x. So that's a good just formula to have in your brain. What does it mean? It means I'm taking the derivative of this function f, this kind of the second step function that I identified earlier, and I'm plugging in the output of g to that f prime. So if we think about our kind of arrows here, it's like derivative is total change, basically, right? So like what's the change, the total change in my output function, my total output function, square root of this guy, square root of x plus x plus 1, when I change my input a little bit. Like, well, first the changing this input affects how the middle step changes, and that's sort of represented by the g prime here. There's a change, how g changes depending on x, that's like the g prime. But then that amount of change sort of gets magnified, multiplied, by whatever change is happening at the step 2, the f step. So f's change, when you wiggle its input a little bit, ends up getting multiplied by g's change when you wiggle its input. That's a good way to think about it. G's input happens to be x, so when I wiggle x a little bit, I get g prime of x, but f's input is g of x. So in order to kind of think about how f changes when you wiggle its input, I have to see how it wiggles at the input of g. So that's like the chain part, is you're kind of chaining the functions as you go along. If my sort of intuitive thing about the wiggling doesn't really make sense, don't worry too much about it. The main thing is to be able to do this as long as we can identify the different pieces. So let's look at this particular example. So we have the square root of this inside function, right? So I'm going to first write down like one way to do this is to explicitly like identify what your f and your g are, and then assemble all the stuff together. I'll show you in a minute maybe a kind of shortcut, but this is totally fine. I want to identify the inside function. We've already kind of done that. That's g of x, my x squared plus x plus 1. And then f of x is square root of x. But that's kind of the tricky part, right, is how do I know to write square root of x? You should think it's like the outside function is square root. But square root of what? Well, of whatever the input is, and we just call that x. It's kind of confusing because there's lots of x's going around. But remember the plan, the only thing that has to work is that if I put the two functions together like this, I get back the one that I'm starting with, right? I want to, the reason I'm picking f and g so that when I put them inside each other like this, I get the formula, the total formula I'm expecting, right? And you can always check that what you did is right, because f of g of x, that means f of x squared plus x plus 1, that's g of x. But f of something means, look back at my formula for f, plug in my input wherever there's an x. So it's square root of x, so I plug in my input in place of that x. Alright, so the x is always abstractly just representing like what is the input. When we do nesting like this, the input will be some other function which might have more x's in it and stuff. But we're still just plugging that in wherever there was an x. Okay, you don't really need to do this step. This is just like checking that what you did worked, but it's good to know. So this is like a maybe in parentheses, check if you want. Okay, so we have our f and our g. We just have to take some derivatives and plug everything in. So what's f prime of x? Well, I need the derivative squared of x. The easiest way to remember how this one works is, right, square root is annoying because it's a square root, but I can always turn the square root into an exponent. So we have to remember that square root of x is the same as x to the 1/2. And then I can use my power rule. So I have x to the something, so I bring the something out in front, and then I have to subtract 1 from the something. So you get minus 1/2. So that's my derivative. And then g's derivative is going to be a little easier. It's just x squared plus x plus 1. Sorry, I think that got erased. X squared plus x plus 1. So g prime will be 2x plus 1. Now we just have to assemble everything together. So f prime of g of x times g prime of x. Just write everything down. F prime of g of x. So here's f prime. I gotta plug g in as the input. So g is gonna go here. That means g is gonna go in the place of this x. So you basically just start writing down the formula for f prime, but everywhere you see an x, you're gonna put a g instead. I like to sort of put it in parentheses to like remember that I'm gonna plug something into here. I could write g of x, but I know what g of x is, so I might as well just write what it is, which is x squared plus x plus 1. So that's this part, and then we still have to multiply g prime. Here it is. Again, you should use parentheses. If I didn't use parentheses, it would look like this, and that would be confusing because it's, is it this times this and then plus this, right? But you know you really mean this, right? So there we go. So that's our derivative. It's helpful if you haven't done this for a while to write some, when you do your examples, like write it out super explicitly like this. But I'll just remind you that you can also do it kind of quickly once you know what you're doing. I would first maybe write our original guy as x plus x plus 1 to the 1/2, right? Just because we know we're going to take a derivative in a minute, so we should put everything into the exponent form. How can I do this derivative quickly? Well, I just like to think of like a black box, right? This is just some black box function. I know how to do the derivative of x to the 1/2. We just did that a minute ago. So I do like, okay, the derivative of black box to the 1/2 is 1/2 times my black box to the negative 1/2. So that's the same power rule that we did earlier. But then and that's this here, right? As long as, because my black box was x squared plus x plus 1. So that's what this is going to be. So we've already done that part. So what I just have to remember that after I do that, I also have to multiply by the derivative of whatever the black box is. So here our black box was x squared plus x plus 1. So that's going to go here. I can fill everything in. And the black box prime, well, it's something prime. Black box was x squared plus x plus 1. Okay, so it's 2x plus 1. So you get the same thing. I will say that I'm not at all doing anything different with this method. I think just for me and for a lot of students, just thinking of it as this black box, I think kind of helps. But really, like, G is the black box, right? When I say black box, it's just another name for G. I'm just not writing G of x here. I mean, when you see this, you should think of this G of x as, you know, black box. There's some function of x. Okay, so let's just see a little bit quicker example of all this on the next one. I want to do the derivative of e to the x squared. By the way, just a side note, if I ever write, or if you ever see e to the x squared, this could mean just looking at it, it looks like it could mean two different things, right? Maybe it means e to the x squared, or maybe it means e to the x squared, right? It's actually not obvious just looking at it, and those are different. If you try plugging in some numbers, you'll get different things. So this is just a pure notation convention thing. Math people and books always mean this one and not this one. If they mean the one on the right, they will make it clear with the parentheses. The main reason is that, like, this expression with the parentheses, because of exponent rules, it's actually the same thing as like, it's e to the x times e to the x, right? That's what squared means, which is e to the x plus x by exponent rules, which is e to the 2x. So it's like, if you really meant e to the x and then squared, like, you would just write e to the 2x, if that's what we really meant. So we kind of reserve this notation to mean the first one. It's kind of like a PEMDAS, you know, it's just like a convention, but you have to know it or else you'll get confused. By the way, you could imagine kind of doing this forever, or not forever, but a couple more steps, like 2 to the 3 to the 4 to the 5. And again, this always actually means 2 to the 3 to the 4 to the 5, whatever that is. But that means 2 to the, right, 3 to the 3 to the 4 to the 5. As opposed to like 2 to the 3 to the 4, all to the 5. Those mean different things. Okay. But not that big of a deal, but just saying, because this is written without the parentheses. I'll try to write it with parentheses if I'm giving you a problem, but you might see that. Okay, any case, how do we do the derivative of this? Well, I identify the black box inside function. It's probably this guy, right? I know how to do the derivative of e to the something. So the derivative of e to the something is e to the something, just like derivative of e to the x is e to the x. But then I have to remember to multiply by the derivative of the something. Okay, so it's e to the black box, e to the g of x, e to the inside function, because that's my derivative, and I could write this if I want. And then I multiply by the derivative of my inside, which is 2x. So it's pretty quick once you feel good with spotting sort of the inside function and taking some derivative. Okay, so just want to point out right away, what is this good for with two of the antiderivatives? Well, before we were talking about, like, okay, I know this derivative, so maybe I could do that antiderivative. But now we could do even more, right? Now I know that the derivative of e to the x squared is e to the x squared times 2x. So I could do this antiderivative, integral. If I see out in the wild integral e to the x squared times 2x, then I already actually know this is just equals e to the x squared, because I found an antiderivative. And like, if I was trying to evaluate this, like plug in like 0 and 1 or something, I would just have to plug in 0 and 1 to e to the x squared. I'd have e to the 1 squared minus e to the 0 squared. So this is cool because before our antiderivatives were sort of like elemental, like basic ones, but now we have something that looks a little more complicated, right? It's like e to the x squared times 2x, so like it's sort of a combination of the two basic functions, but I still know that it's the derivative of something. So if we can kind of imagine starting with this and going backwards to find the e to the x squared, just like algebraically, spotting, hey, this expression is actually the derivative of something from the chain rule specifically. It looks like I did a chain rule because I have some function that I'm timesing by the derivative of like the inside function, right? When you see this, you're like, oh, 2x is the derivative of x squared. So that looks like 2x, x squared was like an inside function that I did the chain rule and I did times 2x, right? You're kind of spotting that that's what's happening. So that's the idea of U substitution, reversing this process, reversing the chain rule process. So let's look at some example right away. So this is very similar to the one we just did, but let's just say we had this antiderivative that we're trying to do. So I'm like, okay, what could this antiderivative be? Thinking about the chain rule. Well, I spot that this x squared is kind of like the derivative of x cubed, right? I know, I'm kind of thinking off to the side or in my head, that x squared's derivative, or x cubed's derivative, is 3x squared. And so there's a connection between x cubed and x squared. I know that that's the derivative. So that's a hint that there's a chain rule happening. You spot that one part of the integral is the derivative of another part of the integral. Okay, so now with that information in mind, I try to come up with, can I find a big F so that its derivative ends up being my inside function, or sorry, my integrand, the thing I'm trying to take the integral of. Chain rule in mind, right? So, kind of just have to think about chain rule backwards, right? When I did the chain rule, we, sorry, there should be a prime here. When I did the chain rule, I have like a product of two things, right? I ended up multiplying by the derivative of the inside function. I identify an inside function, and I end up multiplying by the derivative of the inside function. So here we're going to identify an inside function and sort of divide by its derivative instead, right? I can think, okay, what could my inside function possibly be, right? Probably this x cubed thing, right? We're thinking, because in the chain rule we multiplied by the derivative. So here we have this x squared getting multiplied on the outside. So that probably had to be the g prime, right? G prime of x, the thing we multiplied on the outside, had to be x squared. And so my original g had to have been x cubed. Now this is not quite right because of the 3 here. So to think about that a little bit carefully, right? If x cubed goes to 3x squared, how could I end up at x squared exactly, right? Well, we know that if I'm multiplying by a constant, I can do that before or after the derivative. So I could divide by this constant ahead of time. Then you can just check. If I power rule this, okay, 3x squared, the 1 over 3 stays out front, because that's one of my derivative rules, and then the 3's cancel and you have x squared. So if I want to like negate having the 3 after the derivative being multiplied, I can just divide by the 3 before taking the derivative. So that means our sort of original inside function kind of maybe should be x cubed over 3 or something like that. So yeah, so we kind of identify this g prime. We should identify the f also. F of x is probably, well, it has to be the e part, e to the something, and I'm going to put the inside function there. Right, so it's probably e to the x, because then if I do f of g of x, it's e to the g of x, e to the whatever g is, but I just identified g was x cubed, so I'm identifying that this whole inside thing is actually f of g of x. Or yeah, f prime of g of x, I guess. Sorry, yeah. So we want the yeah. This is a little bit confusing because it's e, but if f of x is e of x, then also f prime of x is e of x, and we really want to identify like f prime of g of x, because that's like the thing on the right hand side. In this case, it's the same because it's e to the x. It's its own derivative. Okay, so sorry if that was confusing. So, right, we've identified f prime of g of x times g prime of x. Right, in our case, that looks like e to the x cubed, that's this guy, f prime of g of x, times x squared, and that looks exactly like our integrand, right? We know that by the chain rule, this expression like is the derivative of something, which means that this something, this f of g of x, is the antiderivative of this expression. So what is our f of g of x? It is e to the x, that's our f of x, but I'm plugging in g of x, and so that looks like e to the x cubed. Okay, so there's kind of like a lot going on here, and it's pretty confusing. And there's an awesome way to streamline this, but I just want to give you an idea of, you could kind of piece this together yourself by like thinking pretty hard about the chain rule. So let's see like a more streamlined way to do this. So basically, by trying to think really hard about doing the chain rule backwards, you could come up with this method, but there's a really common sort of streamlined method that people use. So let's write it this way. So our original function was x squared e to the x cubed dx. So this is where the name u substitution comes in, and I'm usually just going to say u sub. For a tradition, people use the letter u, but the u is going to play the same role as the g. We're identifying an inside function, and I'm going to call that inside function u. So let's write u. You always start by writing u equals, and then you have to pick the inside function. We'll see some examples of like how to pick a good function, but for now let's just trust the process that it's going to work out well if we pick u to be x cubed. Okay, so the way this works is first you write down u equals, and then you immediately write down du equals. Now, you should probably really be writing du dx equals, which means take the derivative of u with respect to x. So let's see that. That's 3x squared, right? For the sort of historical reasons, and also for doing it by hand quickly, it is super duper common to actually write this instead. So you go straight from here to here. We write du equals. Then you take the derivative of this, and then you write dx. It kind of looks like you multiplied this dx over from this middle version. There are sort of things to be said about this. Like the du and the dx are not really numbers, or you can't really split up the fraction like this. But in certain situations, just as a notation, it's useful to write it like this, and you'll see why in just a second. Ask me if you're curious about like how legit the notation is, but it works for doing u sub problems at the very least. This is a really common method. So you start by writing this, then you write this, and now we're like kind of almost done. The idea is to look back at your original integral and identify where the u is and where the du is, and plug the stuff in. So for example, first of all, this x squared, I'm just going to leave it there for now. E to the x cubed is u, that was the whole point. And then I have dx. I want to turn everything into u's here. The plan is to make this an integral just with u's in it, and like a du instead of a dx, and that's going to be like an easier integral, is the idea. So I need to get rid of all the x's. I can't have any x's left. I can't even have dx left. So I want to identify what dx is, sort of using this equation that has dx in it. My favorite way to do this is to actually take this equation and like solve it for dx. Again, it's sort of not legit to do algebra on the du and the dx like this, but in the case of u sub, it works and is a common method, so it's fine, don't worry about it. So if I like solve this for dx, what does that look like? I take my du on the right hand side, and I divide over this guy, right? 3x squared. So I like to do it this way, because now I have dx equals, I have a dx here, so I'm just going to replace that dx with what I found, which is du over 3x squared. Now, lucky me, this x squared and this x squared are going to cancel. So that canceling is the whole entire point, and you're always looking for that canceling at the very beginning. I know that whatever I pick for u, I'm going to take its derivative, this 3x squared, I'm going to end up dividing by that. So if I see this x squared out front, and I see this x cubed here, I'm like, oh sweet, if I take the derivative of x cubed, it's going to be 3x squared. If I end up dividing by 3x squared, then this x squared is going to cancel. That's like what you want to spot when you're looking at the beginning, if this is going to be a good u sub or not. Notice that even though this is more streamlined, it's sort of the same ideas we were doing up here, right? We want to identify like what the inside function was, so that if I divide by its derivative, I can cancel something. That's what's going on here. The u is something that if I can divide by its derivative, it'll get cancelled. And that is very commonly also like, it looks like an inside function, like e to the something. Okay, so let's finish this out and see what happens. So the x squareds cancel. What about the 3? Well, it's a 3 in the bottom, so that's the same as 1/3 times everything. Right, so I could write this as like x squared e to the u. Oh, well, yeah, let's write it like this. If you like, you can imagine shifting over that denominator, right? It's the same thing. That's how fractions work. You can imagine this equally over 1 right here. But then it's a little bit more clear that these x squareds are going to cancel. I have a 3 in the bottom, so just to make it super clear, right, it's like 1/3 times e to the u du, right? But I can always pull a number out of the front of the integral. So usually from here, I'm just going to jump straight to 1/3 e to the u du. Because the x squareds cancel, and there's still 3 on the bottom. 3 on the bottom is the same as 1/3 out front. Right? Okay, so although the original integral doesn't look like something I could take the antiderivative of right away, this integral does look like something I know the antiderivative of. I know that e to the x derivative is e to the x, and even though I'm using this letter u, it doesn't matter. Like, it's still just a variable. The derivative of e to the u is also just e to the u, which means its antiderivative is also e to the u. So here, my antiderivative of e to the u is just e to the u. So this, I kind of resolved the integral, I got rid of the integral sign, I got rid of the du, and what's left is the antiderivative. And I'm super happy. As a last step, I want to plug the u, this u, that I found originally, back in. X cubed. So we can always double check that this works, right? If I take 1/3 e to the x cubed, if I take its derivative, keep my 1/3, chain rule says I do the derivative. So the derivative of e to the black box is e to the black box, from my e to the x cubed, but then times by the derivative of the inside, which is 3x squared. So again, you see that the thirds are canceling and the x squared sort of appears. So we sort of successfully reversed that process. This really is an antiderivative. Okay, so that's pretty exciting. We can kind of reverse the chain rule. The hard part maybe is just spotting the right u to pick at the beginning. We'll do a couple more examples. The more examples you see, you just kind of get used to what a good u to pick is. And there's some guidelines we'll talk about. But once you pick a u, it's kind of plug and chug. I will mention that it's not the end of the world if you don't pick the right u. There's only so many u's you could even pick, right? If we think about this integral we started with, it's integral x squared e to the x cubed. This is kind of an exercise worth doing. Just what are all the possible u's you could pick? U could be x cubed, that's what we did. U could be x squared. U could be x. U could be e to the x cubed. U could be x squared, e to the x cubed, just the entire original thing. U could be a part of the original thing, x e to the x cubed. U could be 1, it's technically possible. So, yeah, I mean, there's a lot of options I'm writing here, but you can see they're all just like, there's just different pieces of the original integral, and there's only so many pieces of the original integral. Very, very typically, it's going to be the piece that looks like it's sort of the inside function of part of it. And what you're really hunting for is something whose derivative also shows up, ideally being multiplied by, like as a factor in your integral. So we could try all the du's here, right? This du, you get 3x squared dx. This du, you get 2x dx. This du, you get 1 dx. So you can just write that. This one you'd get, okay, you gotta go to the chain rule again, so I'm gonna do that quickly, but you would get that. This one, ooh, that's product rule, that sounds annoying. This one, ooh, also product rule, sounds annoying. This one's derivative is 0, so that doesn't really work. So you can see, like, some options, like, are probably not going to work. Some options seem kind of complicated. Usually that's not what it's going to be, although it is sometimes. This one is good because the derivative part, which will end up being divided, matches this, right? X squared and x squared. The 3 is not a big deal. The x squared matching is the important part. I'm going to end up dividing by x squared. This one, 2x is not terrible, but when I divide by 2x, again, the 2 doesn't really matter, you'll have a 1/2. I'm just going to be divided by x, basically. The x squared will turn into x, and that's not as helpful as it could be because there's still an x there, right? I'd have like x, and the e to the, this would be weird too, because this is e to the x cubed, so I'd have like x times u, because it's x squared times x. So, you know, this is not getting rid of all the x's like I want to. But this one is getting rid of all the x's. But again, it's a little bit tedious, but you could just literally try all these. If the first one, if you try, try this at first. Oh, it doesn't work. Okay, let's try another one. Let's try this one, right? You'll find the right one eventually. So don't despair if your first u doesn't work. There's usually a couple choices. And sometimes multiple choices even work. Usually there's only one choice that works. Okay, let's try this example right away. So on this one, I'm going to try to go like just quickly, and you can see how it's not too bad once you get used to it. So I see this integral. I'm like, okay, I need a u. It's probably going to be an inside function. So let's do that. How do I know that, right? It's square root of something. Usually it's the inside function. Also, when I take du, this derivative is 6x dx. And hey, look, there's a 6x right here. Right, so I know that when I divide by this 6x in a minute, I'm going to cancel this 6x here. So the goal is to be able to kind of spot that quickly. I see, oh, 3x squared, this derivative is 6x. Nice. Okay, so again, I like to solve for dx now. Dx equals du over 6x. And now I just plug all this in to my integral. Just keep the 6x. This is u now, that's the point. I replace the dx with this, du over 6x. And now these are going to cancel perfectly. I'll have the integral of square root of u du. Remember, square root of u is the same as u to the 1/2. Now I can integrate this with power rule. Right? I just have to plus 1. And then I have to divide by the new exponent. You're not done here. You got to plug your original u back in, because I want the answer in terms of x. So just write down your original thing. That's u, right? So that to the 3/2. And again, the parentheses are really good here. Over 3/2. If you don't like the over 3/2 in the bottom, remember that's the same as this. You could flip the fraction and bring it out front. That's fine. Cool. So pretty quick, right? I will mention something. You don't have to do this step. I just kind of like it because it clearly, like, I can just replace the dx. But a lot of people just do this step, and they're like, okay, hey, I see 6x dx right here, and right here I see 6x dx. Right, remember when you multiply, the order doesn't matter, so I could do my square root thing, and then have the 6x dx at the end. And so I could like literally replace this 6x dx with du. So if you like that better, you can do that as well. When you do that, when you do this method, sometimes it's easy to like not realize, oh, am I supposed to divide by 6, or am I supposed to multiply by 6? But that's why I kind of like this one, because it just, the algebra just tells you, oh, you're supposed to divide by 6. For example, like, it doesn't always happen, but you know, if you had somehow had like 3 times du equals 2x dx or something, like if that was the equation you started with, then it's helpful because you're like, okay, this is 3 du over 2x, and so it's, you know, 3 over 2x du, and so like the 3 over 2 showing up might not have been obvious like from here. Don't worry too much about that. Okay, I want to do another couple examples. So let's start with this one. So one thing I want to talk about is how would I know it's a u-sub problem? Sometimes I'll tell you. Sometimes it's sort of like jumps out that one part of it is the derivative of another part of it. Right, that's what happened here. 3x squared plus 1, its derivative is 6x. Ooh, good u-sub. This one, x cubed, its derivative is something x squared. Ooh, cool, right? Here, oh, x to the 4 plus 5, its derivative involves x cubed. Cool, probably u-sub. Probably u equals x to the 4 plus 5. Another reason, which reinforces this reason in this problem, is you kind of want u to be the annoying part of the problem. Like here, look at this one. It's x cubed times something to the 10, right? No way I'm going to be multiplying out this thing out. I mean, you could do it, but it would take like 10 minutes, right? And it would be super annoying. So I would really, like, if this integral was just like x to the 10 dx, right? That's easy. I can do that. X to the 11 over the 11, no problem. But all of a sudden it's x plus 1 to the 10, and it's like, ugh, it's horrible, right? Because I have to multiply this out, and it would take forever. So another reason to think about u-sub is like, oh, if only this was just an x instead of x plus 1, that would be awesome. Well, guess what? You can make it a single variable if you want. I can have it just be a u instead of an x plus 1. Right? The plan here is I'm going to write u to the 10 du is like what I want, what I'm imagining. Because that's easy. That's like this one, right? So the only thing stopping me from doing that is I have to do the u-sub thing correctly. So here I do du 1 dx, so that's just dx. So in this case, I can actually literally erase these marks. This is literally equal to this. I replace the x plus 1 with u to the 10, replace the dx with du, and then this is easy. It's u to the 11 over 11, and plugging it back in, it's x plus 1 to the 11 over 11. So that works. But you do have to be a little careful and actually follow this procedure here correctly, because it's not always like this. For example, if this was like 2x plus 1 inside, I still would rather that be a single u like this. I prefer that, because I can do my power rule. I'd have to make u be 2x plus 1. Ooh, that changes my derivative now. Du is 2 dx. So again, I can solve for dx. dx is du over 2. So I can replace this dx with du over 2. And that actually changes the integral just a little bit, right? Because there was this 2x on the inside, I ended up having to divide by this 2 here. I'm going to get 1/2, and then I'm going to have u to the 11 over 11. So pretty similar to what we had before, but you have to be a little bit careful. I can put 22 on the bottom. You have to be a little bit careful with the exact numbers, depending on what the integrand is. But that's another reason for u sub, is I really would prefer this part of the integral to be something simpler. So both of those factors are at play in this problem, because not only is this x cubed the derivative of this inside thing, basically, but also I really would like this inside thing to be a u instead, u to the 10th. So those are two strong reasons to think that this is the right u to pick. Okay, so let's just see what happens. Du is 4x cubed plus 0 dx. And again, I like to solve for dx. So du over 4x cubed. Now we come back here, keep the x cubed for the moment, replace this with u, that was the whole point, still to the 10. Now dx is du over 4x cubed. Okay, cool. So like we've seen a couple times, these x cubes are going to cancel. I have a 4 on the bottom, so it's the same as a 1/4 out front. I have u to the 10 du. And I'm super happy, right? I can just proceed to do my power rule, u to the 11 over 11, and I just have to plug my original u back in. So x to the 4 plus 5 to the 11, and then I have 4 times 11 on the bottom. Cool. So yeah, you want part of the integrals to be the derivative of another part. You want to look like an inside function, and sometimes you want, like, I prefer this to be something to the 10 instead of plus 5 to the 10. So some combination of those reasons can tell you it's a u sub. So I think the only thing we haven't done yet is what happens when there are bounds here, right? So far I've only been doing just this integral sign, which if there's no bounds, right, just means find the antiderivative, which is what we've been doing. But if there are bounds, it means I gotta do fundamental theorem of calculus, I gotta find my antiderivative, and then plug this stuff in. So I would just think of this as first do sort of the regular antiderivative part, right? I'm finding an antiderivative of the inside function. Whatever this is will be my big F that I'm going to plug in, and then we'll plug in the numbers. So first, let's just think about this u sub. So again, I'll let you think for a second. Why would this be a u sub? And what would you want to pick for u? So maybe pause and think about that in relation to what we did before. So here, there's several things, right? There's the inside function here. It would be convenient if that was a u instead, so u squared. And its derivative is also here, 2x. So that's awesome. So I should probably pick u is x squared plus 1. I write down du right away. It's 2x dx. And I might as well solve for dx right away. It's du over 2x. Now I come back to my integral, plug everything in. 2x over u squared, right? That's the point. And then dx is du over 2x. Beautiful, those cancel. This is 1 over u squared du. I have to find the antiderivative. Remember that whenever I have a power in the bottom, that's the same as to the negative power in the top. You pretty much always want to do that conversion when you have something in the bottom, except for this one. This one is log x. It's the one exception. But if you ever have, 1 over x to the 100 in the bottom, you'd really rather that have be x to the negative 100. So here, u to the minus 2, because now I can do my power rule. U to the minus 2 becomes, I add 1, so minus 1, and then I divide by the new exponent. And then in the end, I plug my stuff back in. So, by the way, negative 1 on the bottom is the same as just negative out front, right? And 2 to the negative 1 is the same as like 2 to the 1, but in the bottom, right? And 2 to the 1 just means by itself. So this kind of slightly confusing looking thing is actually the same as this. So let's plug in the u. It's this guy, right? So negative 1 over x squared plus 1. Okay, so all this was like the antiderivative part. That was like finding big F. But we were trying to do this integral, which means I find big F, but then I plug in 2 to big F and 0 to big F. So the way people usually write this is they would write like, okay, here's this integral, and then because equals, maybe scratch work I do this u sub, but then at the end I say equals this thing that I found. But it's not really equals, right? I'm going to plug numbers in. The plan is to plug in 2 and 0. So it's really common to write this notation, this like bar on the right hand side. It just means, it's just communicating, hey, I found a function, and then I'm going to plug in 2 and 0. So this means the exact same thing as taking your expression, but plugging 2 into it. It's good to put it in parentheses. And then subtracting the result of plugging 0 into your function. So 0 squared. Again, you can shortcut some of these steps, right? Like I could just have written 1 on the bottom here instead of 0 squared plus 1, if I can do that arithmetic in my head. But it's good to spell it out carefully if you want to. Now we can simplify. So this is negative 1 over 4 plus 1, and then negative negative is plus 1 over 1. So that's 1, right? So 1 plus negative 1/5, that's the same as 4/5, I believe. So this second part, this was all just fundamental theorem of calculus stuff, right? Once I have an antiderivative, I plug in the top and bottom. So step 1, find the antiderivative, and I might need to use this u sub technique to do so. And then at the end, I write down it's equal to the thing I found, and then I plug the numbers in. I want to mention something about the bounds and the u here. So the way I did it, which is how I usually do it, is go all the way to, like, get back into x at the end, and then plug my original numbers in. That makes sense, and that's a good way to do it. It is somewhat common, some people prefer this method. You actually stop here, don't go all the way back into x. This is helpful because sometimes the x thing is like more complicated. So that would look like, I write down my original integral, and I say, hey, this was equal to the integral of, right, we got to this stage, u squared, u to the minus 2 du, but I want to plug in bounds here, right? So the idea here is that there's like two universes. There's the x universe, and there's the u universe. Doing the u sub is like switching to the other universe. In the x universe, my function is in x, and my numbers are also like x numbers. Right? 0 to 2 means you're plugging in x, right? Here, I plugged 2, x equals 2. And I plugged in x equals 0. So I'm in the x world, my numbers are going to be plugged into x's. When I switch to the u universe, I can do that. And now my integral is all in terms of u. But I can't just use these x numbers, 2 and 0, anymore. I have to use some sort of u numbers in the u universe. Right? When I change from x to u, these bounds, the 2 and the 0, also change. It's actually pretty simple to figure out what they change into. I just have to use my formula, right? If, for example, if x is 2, the top bound, what does that mean for u? U equals what? What do you think? You can use this formula. U is equal to, oh, x is 2, 4 squared plus 1, 17. When x is 2 in the x universe, when I translate to the u universe, that 2 turns into a 17. Which means that this top bound, this 2 down here, would turn into a 17. What happens to the bottom bound? Well, remember, my substitution was u equals x squared plus 1. So if x is 0, then u is 0 squared plus 1, which is 1. So in the u universe, that 0 turns into a 1. So it's legit to write this equal sign, the integral on the left. If I stay in the x universe, that should be an x. If I stay in the x universe and use the x numbers, I get the same value of my integral, the same area under the curve, as if I did this integral in the u universe using these u numbers. Remember, we got 4/5 over here when we did it the other way, so let's just see what happens here, right? U to the minus 1 over minus 1. That's my antiderivative. Now I'm going to plug in 17 and 1. Okay, so 17 to the minus 1, right, over negative 1. I'll just leave it like that. That's the first part. Minus what happens when I plug in the 1. 1 to the minus 1 over minus 1. It kind of looks like a mess, right? But we can just keep going. Dividing by negative 1 is the same as multiplying by negative 1. And the 17 to the negative 1 is the same as 17 in the bottom. So this is really negative 1/17. And then over here, negative 1 in the bottom is the same as times negative 1 in the top. It cancels with this minus sign, so we're going to have plus, plus 1 here, because it's 1 over 1. Okay, so something happened here, because we should be getting the same 4/5 as the end. So let's back up and see if I made a mistake somewhere. Okay, so I looked at it for a second. It's a very simple mistake, so this is totally possible to happen, so you gotta be careful when you do this yourself. I was getting so excited about the U universe that I did my arithmetic wrong. So right here's my thing. U is x squared plus 1. So if x is 2, U is 2 squared plus 1. Right? Not 4 squared plus 1. So that's 5. Okay, so sorry about that. So if we come down back here at the end, this, all the 17s should be 5s instead. So boom, 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 boom. Right? So 1 to 5 instead. I plug in my 5, 5 to the minus 1 over minus 1, I'm going to get negative 1/5 plus 1, which is exactly the same as we got before. So that's 4/5. I was going to mention, before I got distracted by my error, that, right, it's like this going to the U universe thing feels a little bit complicated. Like it's kind of like more than you need, which is why I like to usually just do it this way. Go back into X and don't worry about it. Sometimes it is useful to do it this way because the arithmetic's easier or something, and it's good to know that both exist. But I will mention that, like, the actual arithmetic steps that we do here, like where did this 5 come from? It came from doing 2 squared plus 1, right? I plugged 2 into here. Where else do you see 2 squared plus 1? Right here, right? Where did this 1 come from? 0 squared plus 1. Ooh, that's happening right here. Right, so it's really just a matter of, like, am I doing my changing universes thing sort of before or after plugging stuff in? So it's not really any different. So it's good to be able to understand both ways of doing it. Cool, so that is U sub. Just recap, the generally, if I have a function, or an integral, what I'm looking for is some part of it to be like the derivative of, you know, some other part of it. And that's the thing I want to identify as the U. Right? And you can come up with lots of examples, and you'll have some in the homework. I just want to list like some really common examples that come up a lot. So say I have like sine of x, cosine of x. Super common example, right? U could be sine because the derivative of sine is cosine, and I have the cosine x dx sitting right there. I'm going to end up dividing by cosine when I do this. So again, if I just see sine times cosine, I spot, oh, derivative of sine is cosine. That's awesome. That's going to be u equals sine. By the way, u equals cosine also works here. Maybe try that on your own. Think about it. Okay, what's another common one? Whenever you have like sort of a complicated function, you know, like sine, but with something weird plugged in, that something weird's derivative might exist outside somewhere else. this is often how I come up with a u-sub problem. Like, hey, look at this. Here's a big function with something inside. Its derivative is right here. Boom, easy u-sub. U should be x cubed. Because when I take its derivative, 3x squared dx, I'm going to end up dividing that out right there. There's other examples along these lines, right? Like integral of log of x squared. And then I'd have to times 2x, right? That's another classic u-sub. You could even have slightly more complicated versions of the same idea. Log of sine times cosine. Why is this a u-sub? If I do u equals sine, its derivative is going to be cosine x dx. That's going to cancel. It'll look like log of u du. Now this is not necessarily an easy integral to do, but we'll come back to that later. Some other examples. So these are really classic. Like one part is the derivative of the part. For example, you could have like, sometimes it's hidden. So I could have like maybe log x over x. So this doesn't look like it right away. But remember that the derivative of log is 1 over x. So having this x in the bottom is like secretly having times 1 over x out front. So this 1 over x dx matches that, and it's going to work out. This will become just the integral of u du. One more example of a common type that I'll just mention, similar to what we were doing before. Sometimes you have something like this. Right, like maybe I can do the integral of square root of x, but this is x plus 1, which is kind of annoying. We talked about this earlier, but if I do u as x plus 1, du equals dx, then I can change this to integral u du, and it's all good. So I think of this as like a shifting. Like I have this x plus 1 function. I really like to shift it by 1. So it was just x by itself, sort of. You can kind of do that if you write u equals x plus 1. There's a variation of this, which happens sometimes. Say I have x times root x plus 1. Well, let's just try the same thing. U equals x plus 1, du equals dx. Okay, so we get x times root u du, and then I told you before that you shouldn't have x's anymore, and it's kind of weird we still have this x, and it didn't even cancel. Neither of these two examples was there any real canceling from the derivative part happening. It was just like this shifting into the u coordinates instead. In this case, it actually can work because, right, I'm kind of shifting into the u universe. I gotta think, what is x when I'm in the u universe? What does x turn into? Just like, what do those numbers, those bounds turn into? Well, I look at my relationship between u and x. X plus 1 is u, right? So like, I can solve for x. In the u universe, x is u minus 1. That's actually a big deal because that means this integral, I can replace that x with u minus 1. And now this whole thing is in terms of u. And this may not seem amazing, but it's actually cool because, like before, there's a plus like inside the square root, and that's annoying. I can't do plus inside the square root. But by doing this shift, I shifted u into bx plus 1. It's kind of like I've moved that plus or minus sort of outside. I've shifted it sort of outside the square root. The square root's fine now. We can do that. Maybe just to complete this, remember that u square root of u is u to the 1/2, and then remember we can distribute, right? I can multiply the u to the 1/2 through on both of these things. I'm going to get u to the, right, u times, oh, it's right here, u times u to the 1/2, and then minus u to the 1/2. So we can do exponent rules. This is secretly u to the 1. So 1 plus 1/2 is 3/2. And then minus u to the 1/2. And now you're home free because you can just power rule these. I'll let you try power rule on here. So it's kind of like a little trick, but this does happen sometimes. So another use of u sub is to kind of make this shift happen. So these are, so I just wanted to list kind of some of the more common examples of using a u sub. Trig is really common, stuff with logs, functions inside other functions, and sometimes this shifting. Okay, let me know if you have any questions. Hopefully that was helpful, and I will see you next lecture.